Hello again. This is video lecture 27.2, and we're going to talk about section 2 in chapter 27, where we're going to start looking at circuits that consist of more than one loop. And a loop is any conducting path that current can take from a point around and back to that point again. And any unique way that the current can start somewhere, travel around, and get back to where it started, that's a loop. And the previous video lecture, in the class video, focused on what is called a single loop circuit, which is just literally what the name means. There's one path around. But circuits can, of course, be considerably more complicated than that, and we have to be able to deal with circuits that have more than one loop. That's what we're studying in this video. And one of the things that naturally arises in a multi-loop circuit, at least a multi-loop circuit containing resistors, is a certain kind of resistor connection called a parallel connection or combination of resistors. And I want to talk for a minute about that because there's a way to simplify what's called a parallel combination of resistors down to one equivalent one, and such a simplification can make circuit analysis a lot easier. All right, so we're going to talk about parallel combinations of resistors. So the first thing is we have to be able to identify when we have a parallel combination of resistors. So let's look at the circuit diagram here on the right. We have one important circuit element, a source of EMF, let's say a battery. It's got some EMF curly E with the high potential side and the low potential side shown. And you can think of its terminals as being the points A and B there. And then we have connected right to those two terminals of the battery three resistors. Resistor 1 with resistance R1 is connected to the two terminals of the battery directly. But resistor 2 with resistance R2 is also connected directly to the two terminals of the battery. And resistor 3 with resistance R3 is also connected directly to the two terminals across the battery. That's really what that circuit diagram is saying. And that is a parallel connection of those three resistors. Their top side, here, here, and here, are all effectively connected together. And then the bottom side, here, here, and here, are all effectively connected together. That's a parallel combination of resistors. Notice that if you were to insert any kind of circuit element in here, like in this position, if I put another resistor right there, that would spoil the parallel connection between R2 and R3. You can only have plain old conducting wire connecting them at the top and then connecting them at the bottom. And then they're put directly across something, in this case, a source of EMF. Okay, now here's a very important thing to note. When there's a potential difference, we'll label it V, applied across resistances connected in parallel, the resistances all have that same potential difference V. So in this case, since the three resistors are all connected directly across the terminals of this battery, they must have, all three of them, the same potential difference across them, which is the EMF of that battery in this case. And that's an important thing to know then. Resistors in parallel have the same potential difference. Okay, same V is what that means. Now, it turns out that resistors connected in parallel can be replaced with one equivalent resistance. We'll call it Req. And this equivalent resistance has the same potential difference V that the original resistors had, and the same total current I as the original resistors. Total current. So if we look at our little circuit diagram at the top right, it shows a total current I flowing through the battery part of the circuit. But then what happens when we get to that point labeled A in the circuit diagram is some current ends up going down the first resistor. They labeled that I1. And then some goes down through the second resistor that way. They call that current I2. And some current goes down through the third resistor that way. They label that current I3. And the total current through the battery, I, has got to be the sum of the three currents through the three resistors. That's just conservation of charge. I can't lose any charge anywhere. All right, now, that means, I'm going to take each one of those expressions for the I, and I'm going to replace it with V over its R. That just comes from the definition of resistance. R equals V over I, so I equals V over R. So for that I1 you see there, I'm just going to replace it with V over R1. And for that I2, V over R2, same V. And for I3, V over R3. And that sum there will be the total current. But that will then also be the current through that one equivalent resistor, which you see in the lower circuit diagram. See how we've replaced the three original ones in parallel with the one Req, with the total current I through it. So that total current I is also V over the equivalent, Req. Then the V's all cancel out, and you get an interesting little formula for how to calculate this equivalent resistance for these three resistors in parallel. 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. So it's an inverse sum rule, an inverse addition rule. You've got to take the inverse of R1 plus the inverse of R2 plus the inverse of R3, and that'll be the inverse of R equivalent, and then you've got to invert that to get R equivalent. So that's this formula right here, because this can be generalized to n resistors in parallel. To get the equivalent resistance, you use 1 over R equivalent equals sum, I going from 1 to little n, of 1 over Ri. You have that inverse sum rule. Tip, it is easy to get this equation wrong. Mainly, most people, after they add up the 1 over Ri's and get a total for the sum of the 1 over Ri's, they forget to invert that one last time. So your sanity check, which will often help you if you've made a mistake, is to do this. Once you get the R equivalent, check that it is smaller than the smallest of the individual resistances you started with. If that's not true, you know your Req is wrong. Now, it's somewhat useful to contrast this rule for finding equivalent resistance for a parallel connection with how you find equivalent capacitance for a parallel connection of capacitors. And you remember there, the rule is just add up the capacitances. So like I said in the previous video lecture, the way for combining capacitors in series versus parallel and resistors in series versus parallel are exact opposites. You combine capacitors in series the same way you combine resistors in parallel. And you combine capacitors in parallel the same way you combine resistors in series. And so that's pretty easy to get messed up, unfortunately. But that's the way it works. Okay, so we're going to do a little bit more practicing here with that. But we need more terminology, because if we get more complicated circuits, and note, by the way, I should point out, that circuit diagram in the upper right corner is a multi-loop circuit, because there are, in fact, quite a few different possible loop paths for current to go around. All right, let me highlight a few. First, let me clear out some of the writing on here so it's not so busy. Let me show you one possible path for current to flow around. That one right there. That's one loop. Now let me do another one. That's another one. Okay, I'll do another one. That's another one. I'll do another one. That's another one. Notice it doesn't have to be a loop containing the battery. That's another one. And that's another one. Right? There are a lot of loops for current to flow around. That's a multi-loop circuit. Well, those circuits, as I was saying, get pretty complicated. So we need a systematic procedure for how to analyze them. And for that, we need a little bit more vocabulary. I want to talk about the concept of a junction in a circuit and a branch in a circuit. And we'll use, for the discussion, the circuit diagram you now see on the right. That is definitely a multi-loop circuit. And as you can tell by looking at it, it contains two sources of EMF, curly E1 and curly E2, and three resistors, resistance R1 and R2 and R3. All right, and there's some points labeled in the circuit too. You can see they're just labeled A, B, C, and D. That's for convenience, to help us talk about the circuit. All right, here's the concept of a junction in a circuit. It is a point in a circuit where three or more wires are connected. Three or more wires. So of the points we've highlighted in this circuit, two of them are junctions. The point labeled B is a junction, because there are three wires connected together. And the point labeled D is a junction, because there are three wires connected together. So this particular circuit has two junctions, points B and D. Okay, that's a junction. Next, a branch. That's any path in a circuit between connecting two junctions that does not pass through another junction. Okay? Any path in the circuit that connects two junctions without passing through another junction. We have to be able to identify how many branches a circuit has, and I'll explain why that's so important in just a second. But let's identify the branches in this circuit. We know our junctions are points B and D. How many ways can I go, let's say, from B to D? All right, how many unique ways can I go from B to D? Well, I could go straight down resistor 3 like that. So that's a branch of the circuit. Or I could go left and then down through R1 and then right. That's another way to go from B to D. So that's a second branch. Or I could go from B to the right and then down through R2 and then to the left. And that's a third way to go from B to D. And so that's a third branch. And there is no other way to go from B to D. So this particular circuit has three branches, two junctions and three branches. Why is it so important to know how many branches a circuit has? Here's why. Every branch has its own current. And the current in different branches, the currents in different branches do not always have to be the same. Okay? This circuit then has three unique currents. In fact, they're labeled there. You see them? I1 in the leftmost branch, I2 in the rightmost branch, and I3 in the middle branch. And so it is important to label each branch current, just like that diagram did, and to show a direction for each current, just like that diagram did, even if that direction is just a guess, because you might not always know which way the current's flowing in a branch. You might be able to tell, but you might not. So, but there are only two choices. In some sense, in this case, up or down. So even if it's just a guess, you got to put an arrow in there showing the current and labeling it, and with a direction. And then when we end up solving for what the current is, using algebra, if when we solve for the current we get a negative value, that means the direction that we guessed for that current was wrong. But since there are only two options, since we guessed wrong, then we know what the correct direction is. You'll see how that plays out when we actually start doing it. But here's the key thing. You must know how many branches any circuit has, because every branch has its own current. And that's basically what we have to end up solving for, the current in a branch, in every branch, often. All right, now that's just vocabulary. We still need our physics ideas for analyzing the circuit. And we've actually stated both of them already, but now's the time to consolidate them and put them together. They are two circuit rules. Yes, they're named after somebody named Kirchhoff, but they are the junction rule and the loop rule. And they really are based on fundamental concepts in physics. The junction rule is nothing more than conservation of charge. Electric charge cannot just magically appear or disappear. And the statement of the junction rule is like this. The sum of the currents entering any junction must equal the sum of the currents leaving that junction. That's simple. You got a junction in the circuit. You've identified all the branches in the circuit and given each branch its own current label. Then, the total current coming into the junction must equal the total current going out. That's called the junction rule. It's pretty straightforward to apply. Let's apply it to this circuit diagram. Let's apply it to junction B. All you do is look at your currents, look at their arrows, take the total current going into junction B and set that equal to the total current coming out of junction B. Again, look at the arrows on the currents, not the red arrows on the EMFs, the arrows on the currents. And then look at junction B. Which current or currents are entering junction B? You see which it is? Did you say I2? That's the one, because it goes up to the left and into B. Remember, current does not disappear. So the current entering junction B is I2. What are the currents leaving junction B? Well, here's one going straight down from B. But here's one also that went first from leftward out of B and then down. So the total current leaving junction B is I1 plus I3. So the junction rule says that I2 for this circuit must equal I1 plus I3. The total current entering the junction must equal the total current leaving. Now, if you're curious, why don't you apply the junction rule to junction D and see what you get? Now, what's the current entering? Did you say I1 and I3? So I1 plus I3 must equal the total current leaving, which is I2. And what you end up getting is the same equation that you got when you applied it, the junction rule, to junction B. Okay, so that's one physics idea. That's a key one that we use to analyze a multi-loop circuit, the so-called junction rule based on conservation of charge. And then there's the so-called loop rule based on conservation of energy, which we stated in the previous video lecture. It goes like this. The algebraic sum, with plus signs and minus signs, of the change in potential encountered in a complete traversal of any loop in a circuit must equal 0. And we used that in the previous video lecture, and we're going to be using it a lot for the rest of this chapter. So now with that vocabulary and those two ideas, I'm now going to give you my suggested plan of attack for analyzing circuits. This is how I recommend you approach more complicated multi-loop circuits, okay? This will be our plan of attack for analyzing circuits. It's a series of steps, kind of in the order I have them here. This is how I recommend you approach it. First step, always look for series or parallel resistor and capacitor combinations, and simplify them to equivalent resistors and equivalent capacitors, because that's going to simplify the circuit. So look for that first. Step 2. If the simplification of step 1 reduces the circuit to a single loop circuit, then apply the loop rule and solve for whatever the desired quantity is. When you bring it down to one loop, the loop rule should be all you then need. Step 3. If the simplification of step 1 does not, unfortunately, not reduce the circuit to a single loop circuit, then we have some substeps, and there are several. Ready? Substep 1. Apply the junction rule little n minus 1 times, where little n is the number of junctions in the simplified circuit. And this will in turn generate little n minus 1 independent equations. Like applying the junction rule up above gave us an equation that said I2 equals I1 plus I3. Now you might be a little bit surprised that if I have a junction with, say, a circuit with little n junctions, like a circuit with 2 junctions, why wouldn't I apply the junction rule 2 times? Apply the junction rule once to each junction. Well, it turns out, because it's really just a kind of a zero-sum game, you can't lose or gain any charge, that if you have, say, 2 junctions, and you apply the junction rule to both, you'll get the same equation. I did. I just showed you. So you only really want to apply it once if you have 2 junctions. If you have little n junctions, you get to apply it little n minus 1 times. If you apply it little n times, you'll find that last application of the junction rule will give you an equation equivalent to the ones you already got. All right, so the first sub-step is applying the junction rule little n minus 1 times, where little n is the number of junctions in the simplified circuit. And that gives us little n minus 1 independent equations. Sub-step 2, let's assume that there are capital N unknown currents in the simplified circuit. Capital N unknowns. Therefore, I need capital N equations. But I've got little n minus 1 so far. So now we apply the loop rule, big N minus little n minus 1 times. And between these 2 substeps, you will then have a total of big N independent equations. So in that previous circuit up above, right there, we have, to remind you, 2 junctions, so little n is 2, and 3 branches, each with its own current. So big N is 3. And so to analyze this circuit, which is not just simple series or parallel combinations of things, you could think about that, I would first apply the junction rule 2 minus 1, or 1 time, to get 1 equation. But I have 3 unknowns, so I need 3 equations. So I'll apply the loop rule twice. Junction rule once, in this case. Loop rule twice, I'll have 3 equations. Okay, so I'm trying to give you a general approach. Junction rule, little n minus 1 times, where there are little n junctions. And then loop rule, big N minus little n minus 1 times. Point being, you've got to end up with big N independent equations. Next, algebra. Substep 3, solve the system of big N equations for the big N unknown currents. And that's somewhat easier to say than to do, because the algebra could get messy. And then fourth substep, use your knowledge of the capital N currents to calculate any other desired quantities in the circuit. Okay, we have to practice with this, and we'll be doing that in class. but I'm going to also do a little bit of it right here with you. Let's look at the circuit right there. Let's do a little bit of practice with circuit analysis. Okay, we have a circuit diagram on the right. I see that it has one source of EMF, a battery, with the high potential and the low potential sides labeled. It's got 4 resistors, R1, R2, R3, and R4. And our task is to find the current through the battery. That is the specific current we are to find. And here are the constants. The EMF of the battery, curly E, 12 volts. The resistance R1, 20 ohms. The resistance R2, 20 ohms. The resistance R3, 30 ohms. And the resistance R4, 8 ohms. Okay, so curly E, 12 volts. R1, 20 ohms. R2, 20 ohms. R3, 30 ohms. And R4, down here, 8 ohms. Our job is to find the current through the battery. Notice that that's the current then in this branch right there on the left side, which has been labeled I1 and is going around clockwise, just in that left branch. All right, so look at our steps. Step 1, first look for series or parallel resistor and capacitor combinations. Well, I don't have any capacitors, but look at the resistors. Are any of those 4 are in series or parallel? And books love to draw circuit diagrams with these little differences, like you see how this right-hand branch shows the resistor R3 and then just conducting wire going down here and over here? They love to do that kind of thing. Note that they could just as well have drawn the R3 resistor right here. Okay? And then just put that as a wire up there. That's equivalent to their original drawing. Does that make sense? So, maybe if I draw it that way, do you see any series or parallel combinations? Well, I would say those 2 are in parallel. It's R2 and R3. Okay? So that first step, identify any series and parallel resistances. R2 and R3 are in parallel. So we can find the R equivalent. I'll call it R23, using the parallel resistance rule, which is that inverse sum rule. So 1 over R23 is 1 over R2 plus 1 over R3. So that's 1 over 20 ohms. I recommend you put the unit to remind you it's downstairs like that. Plus 1 over R3, 30 ohms. And then I just think of that as adding 2 fractions. And the common denominator is 600 ohms, the product of 30 and 20. And then in the numerator, I have 30 plus 20, which is 50. Notice the unit is in the denominator. And it turns out that fraction on the right simplifies to 1 over 12 ohms. Now don't forget the last step, to invert both sides. So R23 is 12 ohms, not 1 over 12, 12 ohms. That's the equivalent resistance of the 2-3 parallel combination. But notice that equivalent resistance, 12 ohms, is less than the smaller of the 2 resistors I started with, which was 20 ohms. Okay, so now that I've used a parallel combination of resistors, I can draw a new simplified circuit, which I will do. I'll do it right over here. Still got the EMF that way, curly E, high potential side and low potential side. And then resistor R1 is there. Resistor R4 is there. And okay, away on me. And that's point B, and that's point C. And now between B and C, I have the equivalent combination that keeps going away on me. R23, just like that, R23. And then notice that's a single loop circuit. So, hooray! So just apply the loop rule. Okay? And there's only one loop, and the current, by the way, is I1, going around this way, down this way, and through this way. I1. The I1 you have up above there. Okay? So we're going to apply the loop rule now. So step 2. We have, using a parallel connection of resistors, we've reduced it to a single loop, so we'll use the loop rule. I'm going to start, well, we can start wherever we want, but remember when we do the loop rule, we take on the role of circuit inspectors. And we start at a certain point in the circuit, we pick it, the point, and we traverse around, going back to where we started. We add up the potential gains, subtract off the potential drops. When we get back to where we started, the total must be 0. Well, and I always like to go with the flow, as it were. So I'm going to start, I'll start here at point C. And I will traverse, looks like I have to go around clockwise to follow the current. So the first thing that happens is I go through the resistor R4. So that'll be a drop. So minus I1 R4. Then I go through the EMF in the direction of a voltage gain from low to high. So plus curly E. Then I go through the resistor R1 in the direction of the current, so that'll be a drop, minus I1 R1. And then I go down through R23 in the direction of the current, so yet another drop, I1 R23. But then I'm back to point C where I started, so the total must be 0. There's only one unknown, the current, I1. So we're going to solve for it, just using algebra. It looks like I want to write it like this. Curly E equals I1 times R4 plus R1 plus R23. So, solving for I1, curly E over R4 plus R1 plus R23. The EMF is 12 volts. R4 is 8 ohms. R1 is 20 ohms. And R23, I found, is 12 ohms. That's 12 volts over 40 ohms, and that's 0.3 amperes. And that's the current I1, flip back here, in this single loop circuit, which is also the current in the leftmost branch of the original circuit, which is the current through the battery, which is what I was supposed to find. Okay? All right, now in class, I'm going to do a problem where I can't really do much with step 1. And I'm going to have to, and therefore with step 2, I'm going to have to go to step 3 in that plan of attack. But for now, I'm just going to leave you with another little class engagement. For Blackboard. And here's what's going on. We have a battery with a potential V across it. You can think of that as like its EMF. And it is connected to a combination of two identical resistors. Let's say their resistance is each R. And there's current I through the battery. Okay? All right, then we've got some cases to consider here. First, A, question. What is the potential difference in terms of the V? Now that's the potential difference across the battery. But what's the potential difference across each resistor if they are in series? So let's draw a picture. We've got a battery like that. The potential difference across it is V, and the current going through it is I, and then connected to it are two resistors, identical, in series. So you should be able to draw that in a circuit diagram. It would be like that. Okay? That's the two identical resistors in series connected across the battery. And that's the potential difference across the battery and the current through the battery. So in question A, you are asked for the potential difference across each resistor. And the answer choices are V, 2V, or 1/2 V. All right, then in B, what is the potential difference in terms of the V across the battery for each resistor if they are in parallel? So now let's draw another picture. There's the battery. Again, potential difference V, current I going through it. And now these two identical resistors are connected in parallel with each other, like that, R and R, and then in turn are connected directly across the battery. So now you are to find the potential difference across each resistor in terms of the V across the battery. And the answer choices are V, 2V, or 1/2 V. Then C, what is the current in terms of the current I through the battery, but what's the current through each resistor if they are in series? So now go back to the series picture over here on the left. Now you want to know the current through each resistor in terms of I, which is the current through the battery. The answer choices are I, 2I, or 1/2 I. And lastly, what is the current in terms of the I current through the battery through each resistor if they are in parallel? So now you're back to this diagram over here on the right again. And I want to know the current through each resistor in terms of the current I through the battery. What's the current through each resistor? Again, the answer choices are I, 2I, or 1/2 I. So those are the questions you answer for class engagement. And then we'll be practicing with circuit analysis in class. And that's all for this video.